Welcome to Finding Different Representations of Rational Functions. Actually, the title of this video should probably be better if it was Understanding the Different Representation of Rational Functions, because that's what we're going to take a look at in this video, the different ways you could represent a rational function and how to understand what's being thrown at you. So first, let's talk about the three different representations of a rational function. So first we have graphically, right? Looking at a graph. I give you a graph, you understand everything that you see in that graph. Versus looking at just the function itself, right? Just the f of x equals polynomial on top, polynomial in the denominator. You know, what is just looking at that tell you? And then finally, we can actually understand a lot about how a rational function is going to behave graphically and what the function is going to look like just by understanding limits that are attached to certain different parts, different x values, I guess you could say, of that rational function. So let's just kind of dive right into it. But I want to give you a quick pause here. If you haven't already, please go back and watch the videos over domain, vertical asymptotes, holes, zeros, end behavior, slant asymptotes, because all that stuff is going to be really important to understanding everything I'm going to say in this video. So here is our first beautiful, wonderful graph. Now, I want to point out that the vertical asymptotes that are just jumping at you with these dotted green lines, those are actually not part of the graph. Meaning, like if you were to graph this on Desmos or a calculator, you're actually not going to see those. I put those in on my own so that you could see that they're there. But they're not an actual part of the graph. Just the red lines is the actual function itself. So it is nice when I or your teacher puts those dotted lines in there. That way you know for sure where those vertical asymptotes are. So let's actually comment on that first. So I do see that we have two vertical asymptotes. One clearly at -6. Now the other one is not so clear. It looks like it's a little bit more than 1. So at some point when you do look at a graph, sometimes you just have to make estimates. So it looks to be maybe like 1 1/3. So we'll say 4/3. Definitely looks not quite in the middle. I don't think that'd be at 1 1/2. So it looks like 4/3. We'll go with that. Now, you know, because we have these vertical asymptotes, we know that these are values that make only the denominator equal to 0. So if I'm thinking about what this function is going to look like at the end, I know that in the denominator, I'm going to have a factor of x plus 6. That way, when I plug -6 in, I get a 0 only in denominator. And I'm going to have a factor of 3x minus 4. That way, when I plug 4/3 in, I get a 0 only in denominator. Now, the other thing I noticed by looking at this graph are the zeros, the solutions, right? I see a nice, beautiful one right here at x equals -2. And I see another one right here, which we'll estimate to be at about 1/2. Okay, again, when you look at a graph, sometimes you got to make some estimates. Now, zeros are values that make only the numerator equal to 0. So that means x plus 2 must be a factor in the numerator. And we'll go with 2x minus 1 as another factor that would have to be in the numerator only. All right, so that gets me pretty far with building this function, but I also notice there's something else going on in this graph. I see a horizontal asymptote at approximately 1, right? Now, I don't see the horizontal line drawn in there, but you could kind of imagine it's in there because I do see the end behavior of the right and the left is not going towards infinity or negative infinity. It looks like it is going down closer and closer to a horizontal asymptote. On the right side, it looks a little more obvious that it's going towards 1. The left side, maybe I need to zoom out a little bit more so we can see that that line would continue going towards 1. So I do have a horizontal asymptote at y equals 1. Now, how do horizontal asymptotes affect your function? Well, remember, to understand end behavior, you have to divide your leading terms. And when you divide your leading terms, the degree on top and the degree at the bottom are the same. Hence, your leading terms reduce to just a constant. If that constant value is your horizontal asymptote. So this means that when I divide the leading terms, I need to get a 1. So let's go back to look at our function. Let's actually multiply our function out. So far we've covered the zeros and the vertical asymptotes, guaranteeing us the vertical asymptotes and the zeros that we see in this graph. But if I multiply the numerator, I get x squared. And if I got to do a little bit of multiplication there, I hope you guys are okay with that, I get a 3x and I get a -2. And in the denominator, I'm going to get an x squared, a 3x squared. I messed that up too on top. The top would be a 2x squared when you multiply. I apologize. Bottom would be a 3x squared. I'm going to get a positive 14x and a -24. Now, if I stop right now and say that this is the most likely function for this graph, I'd actually be wrong Because look at those leading terms. If I divide the leading terms, yes, the x squareds will reduce to a 1, so I do get a constant. And when this occurs, you have a horizontal asymptote at that constant. But as of right now, it's 2/3. That can't be. That would be meaning I would see a horizontal asymptote at 2/3. Now I'm going to be honest with you. There could be, right? Like we just estimated that the horizontal asymptote is at 1. It could be a little bit lower at 2/3. So I'm not going to lie. When you look at a graph, there's some things that you're not 100% sure on. So it could in fact be that the horizontal asymptote is at 2/3, but if I'm like, no, the horizontal asymptote is at 1, I'm confident it's at 1, well then all I would have to do is multiply the top by 3 and multiply the bottom by 2. What that's going to do is it's going to guarantee me a 6x squared on top and a 6x squared on the bottom. That way, when I divide those leading terms, I do get 6/6, which is 1. That's going to force the horizontal asymptote to be at 1. Now, multiplying by a constant on the top and bottom is not going to affect the zeros from the numerator, nor is it going to affect the fact that I have those two values in the denominator, -6 and 4/3, that create those vertical asymptotes. So there's a good indicator of what this function could very well be. 6x squared plus 9x minus 3 divided by 6x squared plus 28x minus 48. All right, let's take a look at another one here. Here's another really cool graph where we see a slant asymptote and a vertical asymptote. Now, I wanted to have this zoomed in because we are going to try to determine what this function could be based on looking at the graph. But I also wanted to zoom out. So this is the same function, just zoomed out. My marks go by 10 instead of 1s. So we really get to a nice view of how that slant asymptote affects the end behavior. So the right end is going towards infinity. The left end is going towards negative infinity. I definitely see that for a fact. And I see that they're hugging that slant asymptote as it goes. So that slant asymptote is definitely affecting the end behavior of this function. But I also see that vertical asymptote happening there in the middle as well. So pretty cool function. But the zoomed in view is going to give me a little bit better idea of what these values are. So first off, I notice that I do see a vertical asymptote at x equals -3. So if I'm thinking about what my function could be at the end of the day, I know that there must be an x plus 3 in the denominator because I know -3 only makes the denominator equal to 0. Now, I also see two zeros. I see a 0 at x equals -6, and I see a 0 at x equals 4. So zeros are values that only make the numerator equal to 0. So I have an x plus 6 and an x minus 4 in the numerator. So I could go ahead and multiply this out now and get x squared plus 2x minus 24 over x plus 3. Now let's make sure we check that end behavior because we want to make sure that end behavior rules apply. So if I divide my leading terms, I get x. That is linear. That means I have a slant asymptote. And the overall rational function takes on the end behavior of that linear function, which in this case is just x. So I got that linear function just x. So that is an odd power with a positive leading coefficient. And that is why we see the right side is up and the left side is going towards negative infinity. Because remember, that's what an odd power polynomial with a positive leading coefficient is going to be for end behavior. But let's actually find the actual slant asymptote because we do know that the slant asymptote is going to be parallel to this value. So when you divide those leading terms and you do get a linear function like I did here, your slant asymptote is going to be parallel. So my slant asymptote is definitely going to have a slope of 1. But let's actually find the equation of that slant asymptote. So I can clearly see that the slope is 1. So if I start at any point, I go up 1 over 1, up 1 over 1, up 1, right 1, up 1, right 1. But I do see that the I'm drawing a blank here. The y-intercept is -1. So my slant asymptote is going to be 1x minus 1. That is the equation there. Now, let's confirm that that would be true here. Now, remember, to find the actual equation of a slant asymptote, give it a function, you need to do a little synthetic division. So I have 1, 2, -24. I'm going to put the 0, the value that makes the numerator's, the value that makes the denominator equal to 0 on the outside. Drop down the 1, -3, add, I get a -1, multiply, I get a +3, add, I get a -21, the remainder is not needed at all. Boom, there is my slant asymptote, 1x minus 1. So it does confirm that the function I created actually does in fact make that slant asymptote. Now I do want to make one more point about this graph. Remember, if you were to graph this function in Desmos or on a calculator, you're not going to see these dotted lines. So you're actually not going to see the slant asymptote or the vertical one. You need to imply that they're there. And that's why, as a teacher, when I add them to the graph, it makes it a little bit easier to see them and understand where exactly they're at. All right, let's move on to the second type of representation of a rational function. That is the actual function itself. So the list of questions I could ask you here is so very long. Let's start off with domain. So the two values that make the denominator equal to 0 are -5 and +5, because I do see that it factors there. So the domain of this is going to be -infinity to -5, -5 to 5, and 5 to infinity. Sorry for my messy handwriting there. Every value other than 5 and -5 affect the domain. So every other value is good to go except -5 and 5. All right, the other thing I could figure out is end behavior as well. Remember, all I got to do is divide the leading terms. So if I divide the leading terms, I get a 2. Now that's a constant, right? That means I'm going to have a horizontal asymptote at y equals 2. My degrees are tied. So when I divide the leading terms, I do get a constant, and that constant is your horizontal asymptote. So this tells me that my end behavior to the right and to the left, towards positive infinity, towards negative infinity, is going to be 2. All right, what else? Now to find zeros and vertical asymptotes, I got to do a little bit of factoring. So let me see if I could factor this numerator here. I actually already factored the denominator, so I'll do that first, I guess. X minus 5 and x plus 5. And let's see here. I get a 2x, I get an x. Let's see here. What's going to be left? Let's see. Let's do, let's try a 5 and a 2. That's going to get me a 10x on the outside and a 2x. Oh, that's going to do it. Make that a plus and this a minus right here. So there is my 2x squared. There's a 10x on the outside, a 2x, negative 2x on the inside. That makes the 8x in the middle. And negative 2 times 5 is negative 10. All right, so now I realize, x plus 5, that's a common factor from both the numerator and denominator. That's going to produce a whole. All right, so what do I know here? I know I have a vertical asymptote, but x equals 5, because 5 only makes the denominator equal to 0. I have a 0 at x equals 1, because if I plug 1 in, it only makes the numerator equal to 0. So because -5 makes the numerator and the denominator equal to 0, that means I have a whole at -5. Now remember, we need to be able to find the y coordinate so we know where that whole is placed. We know the x coordinate is -5. Where is the y coordinate of that whole? Now to do that, we simply plug in -5 to the two factors that did not get removed. So remember, the x plus 5s, you kind of ignore them for a second because that's creating the whole. And you plug -5 into what's left over. So that's going to be -10 minus 2 over -5 minus 5. Again, I've just plugged in -5. 2 times -5 is -10. Minus 2 is -12. -5 minus 5 is -10. Let's see, that's going to reduce to a 6/5. So 6/5 is the location of that whole. So pretty cool there, right? So again, look at everything I learned and understood just by understanding all the different parts of this function. Now let's talk about that end behavior one more time. So let's just write that out officially. So the limit as x goes towards infinity is going to go towards 2 because that horizontal asymptote. And that's going to be the same for the left end behavior as x goes towards negative infinity. And that is also going to be 2. So pretty cool there. Pretty simple to all the amazing stuff I can learn. All right, now the third representation is understanding a rational function by looking at limits. So first I would have to identify, hey, we are dealing with an f of x, a function that is rational. Here is all the information you need to build this. This is actually a pretty cool problem. It's a pretty challenging one. So let's walk through it real slowly here. So first off, I notice that my end behavior is a horizontal asymptote. As x goes towards infinity, as x goes towards negative infinity, it looks like both ends go towards 3. So that instantly tells me I have a horizontal asymptote at y equals 3. That means that when I divide my leading terms, I must get a constant. So the degrees must be the same. So I get a constant, and that constant needs to be 3. So I got to think about that when I build my function. Now, let's jump down here. As I approach 6 from the right side, that's this little plus sign, and from the left side, that's a little minus sign there, I go towards infinity or negative infinity. That's what happens at a vertical asymptote. Remember, when you approach a vertical asymptote, in which they're telling me that vertical asymptote is at x equals 6, From the right side, I go towards infinity. From the left side, I go towards negative infinity. That is a sign with limits that I have a vertical asymptote. So again, what is a vertical asymptote? It's a value that only turns the denominator into 0. So that means I need an x minus 6 in my denominator to force the denominator to turn into 0. Only the denominator. But again, if this is a graph, we would see that dotted line, right? All right, so the other thing I notice here is I have a hole. How do I know I have a hole? Because as I approach 4 from the left and the right, I am approaching 1/2. That means that there is a hole located at 4, 1/2. As I approach 4 from the left, as I approach 4 from the right, the limit does exist. The two sides are coming together at 1/2, but if it's a rational function, that means that there must be a hole there. So the limit can exist even though at 4, nothing exists. All right, so let's try to kind of put all this together, right? So if there is a hole at 4, that means I have a factor of x minus 4 in both the numerator and the denominator, because that means if I plug in 4, I get a 0 on top and bottom. That's the sign that you have a hole. Now, what I don't know is what this remaining factor is going to be on top, because it did not tell me anywhere what my 0 was. So I'm just going to put an x. I'll put a plus c there for the moment, because I know that there's a vertical asymptote at 6. So x minus 6 must only be in the denominator. There's a hole at 4. So there must be an x minus 4 on top and the bottom. Now, the other thing I know for a fact is that there's got to be a 3 out in front here, because when I divide the leading terms, on top I'm going to get a 3x squared, on the bottom I'm going to get an x squared. I need to get the 3. That produces the horizontal asymptote that I clearly know based on my end behaviors of 3. So here's what I'm going to do here. On top, I don't know what that c value is. We're going to talk about how to find that right now. But here's the trick. How do I find that c value? I know there's got to be a 0 somewhere in this graph, but I was not given any information about what that 0 is. All right, so this is where things are going to get a little tricky, so take your time here and pay attention. All right, so remember, how do you find the hole? You plug 4 into what was left over, and when I do that, I get a 1/2. So I'm going to actually ignore the x minus 4s for a second. I'm going to focus on the 3 times x plus c over x minus 6. Because I know that when I plug 4 into what is left over after that common factor is removed, I need to get 1/2. So I'm going to plug in 4s. If I plug in 4, I get 3 times 4 plus c over 4 minus 6. And when I plug in 4, I need to get 1/2, because I know that's where the location of the y-coordinate of the hole is at. So that's 12 plus c on top over negative 2 on the bottom equals 1/2. And now I just got to cross multiply to solve for c. So I get 24 plus 2c equals negative 2. Remember, when you cross multiply, you got to distribute. 2 times 12, 2 times c. Subtract the 24 over. I'm going to have to move my work up here. I ran out of room, sorry. So I get 2c, and I subtract. I get negative 26 when I have that c there, right? You follow me? And divide by 2, divide by 2. So I get c equals negative 13. So that I know that this remaining factor right here must be x plus a negative 13, which I could write as x minus 13. So my final function would be 3 times x minus 13. That means there's a 0 at 13. Times x minus 4 over x minus 6 times x minus 4. This is guaranteeing me the hole at 4, 1/2. It's guaranteeing me the vertical asymptote at x equals 6. And it's guaranteeing me that horizontal asymptote at 3. And I now know that I have this 0 solution as well at 13. So pretty cool that I can learn all that. Once again, how do I know about that horizontal asymptote from my end behavior? How do I know about that vertical asymptote? Because when you approach a vertical asymptote, you go towards infinity or negative infinity. And how do I know about that hole? Because if the limit exists as I approach 4 from the two sides at 1/2, but nothing is actually there, because if you plug in 4, you get a 0 on top and bottom. That's not in the domain. That tells me that there's a hole there. That means that the y-coordinate there would be at that 1/2. So pretty cool there. Pretty interesting stuff. All right, let's try one more here. And you know what? Maybe you want to do is actually pause this and then jump forward and see if you got it right. You know what I mean? So could try it out. All right, so what do I know about this function? All right, so the end behavior is at negative 2. The right side and the left end behavior both go towards negative 2. So I have a horizontal asymptote, but y equals negative 2. As I approach 5 from the left and the right, I'm going up or down. I can actually draw that. That's going to be a vertical asymptote at x equals 5. The right side is towards infinity. The left side is towards negative infinity. So I know that when I'm building this function, I'm going to have an x minus 5 in the denominator only. Let's see here. Oh, because there's a horizontal asymptote, I know that my numerator is going to need to have a negative 2 out in front there. That way, when I divide the leading terms, I get a negative 2 as a constant, forcing that horizontal asymptote. Oh, I also realized I have a hole, because as I approach negative 2 from the right and from the left, I do have a limit existing at 3. But when I plug negative 2 into the function, I get nothing. It's not in the domain. And holes occur when you make both the numerator and the denominator equal to 0. So I have that x plus 2 on the top and the bottom. So if I try plugging negative 2 into the function, I get does not exist because you can't divide by 0. 0 divided by 0 is 0. But because it makes the numerator and the denominator equal to 0, I know that I'm going to have a hole there. So the only thing left is what this remaining factor is. I'm going to put an x plus c there. I don't know what it is. It must be where the 0 of my graph is. So let's put everything together here. There is my final function. The only thing missing is where that solution or that x-intercept or that 0 is. I'm going to ignore the x plus 2's for a second because that is where the hole is at. And I know to find the location of the hole, which I already know is 3. I already know the location of the hole is 3. But if I plug negative 2 into what's left over, that is what produces that 3. So I'm actually plugging that negative 2 in, and now I got to solve. So I get positive 4 minus 2c over negative 7 equals 3. Multiply the negative 7 over, and I get negative 21. Subtract the 4, I get negative 2c equals negative, let's see, if I subtract the 4, I get negative 25. Divide both sides by negative 2, and I get a c value of positive 25 halves. Or that is exactly 12.5 if you like. So my remaining factor up top there would be x minus x plus 12.5. That's c. C is actually what I solved for. And that means that I have a solution or 0 at negative 12.5, because that way negative 12.5 would only make the numerator equal to 0, producing a solution. So pretty cool that you can learn an awful lot about what your rational function is doing based on knowing some of the limits at different values here. So pretty longer video here, but hopefully I went through the different representations and how you could really learn so much about every aspect of that graph, whether you're given the graph, you're given the function, or you're even given some limits. So a little bit of work to do, but hopefully it was all pretty easy. But highly recommend you watch all of the videos thus far in rational functions to kind of piece everything together in this last video.